Hello everyone. It's slightly early, but I asked people to be early for the picture. It seems the photographer is not with us yet, but it's okay. We all have a super high-end camera in our pockets because we paid too much for an iPhone or similar. So I think we can we can do the picture ourselves. So people who would like to be in this year's IWACO group picture, please move forward, and we'll take the picture now. And we'll start with right after we'll have James' keynote. Take it away.
All right, joining us now or talking now is James about difficulties with Rust ownership and how to solve those with old ideas from object-oriented ownership. Take it away.
Something like that. How do I play this? Just trying to remember how many years there's been IWACOs. We don't run them every year, but anyway, if you do borrowing on the conference, this is what you get. I've just realized, and there is that Al Pacino playing Shylock, famously in Shakespeare's play about the bad things about borrowing. But in spite of that, and I did notice I haven't really had a chance to look at the other papers yet. There's at least one paper on a borrowing calculus and another one from borrowing from SEP logic, all these sort of things. What am I talking about in about 30 minutes or so? I'm going to start by talking about the wood from the trees, which is an English phrase. I believe the American phrase is the forest from the trees. Hopefully I'm going to talk a bit about borrowing versus ownership and maybe where we can go with Rust or with other languages. So here's currently my favorite short Rust program. And the question is, what's the lifetime of that borrow? In another life, when I had a teaching job, I actually gave this as an example in the class, just, I don't know, because I'm perverse. But that Rust I can give it away. Rust will actually accept this. What's the lifetime of that borrow? Because that there, x is a mutable variable that is a borrow of, as Rust would say, a borrow of the box of I size. Yes? It has two lifetimes, yes. I was very nearly going to say, you could even argue it has two lifetimes and then a non-lifetime. So I was going to say, you've all got the answer right because nobody's answered because there isn't actually an answer to the question. What's going on here? Now, does it compile? The answer is yes. What actually kind of happens is it's almost as if the declaration was moved for all effective purposes, was duplicated and then moved inside each of the curly brace blocks that we can see here. Okay, so in that sense, you're quite right. There's one lifetime here. There's another lifetime here. And when I say there's a non-lifetime, is if you try to do anything, well, unless you put in extra code to assign to X, at which point it would get a third lifetime, There's not really any lifetime for X within here or within here. If there are any ox-camel people in the room, please tell me your language won't accept this. Because I've had to explain to somewhat, motivated final year students about why you might want a language and why you might want to do this, and we just all kind of want to curl up in the corner and cry. And I guess underlying this talk is that how we think about programs and how we think about what we tell people about programs is important or possibly more important than the details of the thing. Should this compile? Well, personally, I think no, but I think a more interesting or an important question is why? How do we know what basis would we have for making arguments as to why our language design should support this or shouldn't support this? So, there we go. First takeaway, I don't know if this is the first takeaway, this is a wood. Whoops, sorry, oh God, now I'm going backwards. No, I'm not. Right, this is a wood. Any idea which wood it is? I'm from New Zealand. You've all seen Lord of the Rings. If you fly to New Zealand, because it takes 10 hours or 12 hours to get there from here, there's, I believe, a law that says Lord of the Rings has to be installed on all the seat-back entertainment systems, and you're required to watch them if you haven't already when you fill in the quiz on your arrival card. Okay, that's a joke. But anyway, this is a wood in New Zealand, and it's called a goblin wood. And, it's got all these kind of cool trees. I think that one looks like an ent. The actual wood sequences, if there are fans of the Lord of the Rings films here, it was our economy for a number of years. Excellent. We need your continued investment in merchandise to keep our country afloat. This is why I don't have a job anymore. No, but although this is what New Zealand woods actually look like, the actual woods in the film was shot in a leaky warehouse next door to Wellington, well, not quite next door to Wellington Airport, but not very far away. That was all a stage set. That's the wood, and it's a pretty cool wood. Or rather, that's the trees in the wood. Because the wood is pretty cool, but here's what it looks like to NASA. That wood is literally a wood called goblin wood. It's in New Zealand. It's in a province called Taranaki, I guess, and that is Mount Taranaki there, seen directly from the top. There's obviously snow on it, and there is the wood, or the forest, and it's a circle. And that's kind of important. And in fact, if you're a fan of Lord of the Rings or The Hobbit, you'll know there's actually quite a lot of time when the characters do wander around a wood and get stuck going round and round in circles. And they're not doing algorithms to try and work out whether a linked list is circular. Okay, I can't believe I said that, but anyway. Being able to see the trees is important, but you need to think about the wood. This is sufficiently striking that various people have said, why is it? Is this some weird natural function? Is this due to the biology of the trees? And of course, my answer, because if you ask me on a good day, well, in fact, it doesn't matter whether it's a good day or a bad day. If you ask me a question, I will say the answer is always object ownership. But in this case, it is, because that wood, the goblin wood, is part of a national park. And the national park is kind of co-owned, and whereas all the land around it, that's just standard New Zealand farmland. You can't actually see the cows and the sheep, but that's basically what there will be there. But that wood that is a national park, it's actually owned technically by the mountain, which recently was granted legal personhood. And before you start yelling at me, I'll point out that giving a mountain legal personhood is no worse than giving, I don't know, Microsoft legal personhood. And we're quite happy to do this to corporations, so we may as well do it. There's a mountain, there are a couple of rivers in New Zealand that have legal personhood. Hell, the ACM has legal, for all I know, SPLASH' has separate legal personhood from the ACM in Singapore. I don't know if you had to set up some kind of company so that if it all fell apart, the university wouldn't get sued. But anyway, ownership, that's what gives that the shape. And there is this saying, again, that's actually the Americans. I actually have a song which quotes those lyrics, but apparently I didn't realize the UK version would be not see the wood for the trees, which this kind of has a second meaning, because wood can either mean the actual, bits of wood, or it can mean a wood. The American version, the forest for the trees. We should think about the large-scale structures at least as well as the smaller-scale ones. And if you're going to explain why that goblin wood is there, being able to say things like, well, it's actually a national park. It's a national park that's now co-owned by the Tamanawhenua, the indigenous people. That's why it's this circle, and if you want to go to it, all those things are kind of important to know, as well as the fact that it'll kind of look cool, and you're going to have to thread your way. I didn't get any pictures of the sort of twisty little paths all alike that you would have to find your way through. So, what's that got to do with this? Well, I have a tradition of being somewhat mean to people, but actually, I only put up work from people. I only put up work that I like. For example, there's this lovely paper by Will and Gavin and Sriram, which talks about presenting a conceptual model for how ownership should work in Rust. Well, that sounds good. That's sort of what I'm kind of into. Conceptual models and these kind of things are borrow checking, flow-sensitive permissions, paths into memory. Great. And, you know, they've got some really nice stuff. Those guys have obviously got a great infrastructure in Racket, which they're, is that right? I guess that is actually Rust code, but probably building on that, I don't know. This is much better than things that I remember from 10 years ago, like the, it was called the Interactive Python Tutor or something. And, you know, it shows you there is the stack and there is the heap. But most of the work in that paper, and I think there's a formalization, is a model which has, well, capabilities, which, as Martin reminds us, goes back to, who is it, Dennis and Van Horn in 1966, before even I was born. Although checking their paper, they would actually call these various things, you know, can you read, can you write, do you have ownership, whatever. They actually called those things access indexes or something weird. And the capability is, well, it's a pointer plus all the things that you can do, the effects you can cause through that pointer. So a pointer with read and a pointer with write are two separate capabilities. They may be a capability in some sense to the same underlying state. They may be a capability where doing something on one thing affects something else, but they're basically two separate capabilities with different, well, Unix calls them permissions. I blame some guys that wrote a paper, God, more than 20 years ago, that kind of publicized the use of the word capabilities for those kind of things, and I sort of wish that we'd picked a different word. But anyway, most of the time if I talk capabilities, I will have the capability in the sort of object, a wider capability sense, the same that it was used in capability computers as meaning the unification of an address and the rights that you may have over it. And maybe one or two other things we'll throw in. So there's that. These are diagrams, but I'm going to say these are fine, but they're still about the trees. They're not about they're not even about the trees. They're about the wood. Sorry, they're about the trees, not the big thing. Knowing that, you know, this will tell you, okay, you don't have appropriate permission to do something. And that's important to know, and it's important to know if you're writing programs, and it's important to understand. In the same way, at some level, it is important to understand where, I don't know, the way the bits go, when you add two complement numbers together. Every programmer should understand that. But it seems to me these arguments are operating at that level. Tree borrows, once again, another nice paper that was in PLDI, and they say, well, it's about keeping track of aliases. So here, this is all within one scope. And we can see we make a mutable variable and we take these, well, I shouldn't have said, well, actually they said aliases because I ripped this out of a paper, which is a bad habit I've got, but at least I don't misquote things. So they say keeping track of aliases, but the Rust term for that is borrows. And so these things here are all mutable borrows of a mutable Rust variable. And they do a tree here, which is, well, that's the structure of sort of the way these aliases get established, yeah? And then they have this great FSM, which I really think Ralph should put on a T-shirt, which is, you know, it's effectively the way the compiler or the programmer needs to think about the state of various references and things in Rust programs when they go through. I'm sorry, I'm going to have to speed up a bit, so apologies to Alex, because I was going to say a similar thing about place capability graphs, which is another nice paper. And look, it's got these diagrams. I like pictures. I think at least half the time I kind of think in pictures. And once again, these pictures are about the way to borrow flows. And this one is particularly cool, and I really like, you know, I mean, we really seem to be approaching on Feynman diagrams there. I don't know if, in fact, somehow we are creating, I don't know, an object-anti-object pair in the garbage collector that sort of annihilate and... Actually, that's not a bad idea. Someone remember that for later. Okay, right. That was supposed to take, oh, it has only taken, no, it's supposed to take shorter than that was. Anyway, if these things are looking at the individual participants in our forest, the individual trees, when we take a step back, what is ownership? Well, apparently, according to, again, the Russ book, by ripping pages out of things, I don't have to type the slides myself. I presume most people are familiar with this, yeah, more or less, or no, you're lucky. Sorry, I shouldn't say. You can kind of think of it as C++ with, well, you know, more C++ than C++. Right. There are these ownership rules. Each value has a, well, it says each value has a variable that's called its owner, which I would probably disagree with. The important use there is the word value, not because I think necessarily they do things with values, but that's the way they think about it. And by value, they almost mean a chunk of memory. In other words, it's value not used in the sense you might use, well, in Haskell, but it's a value in the sense that, once again, you might use in C++, or to step back, C, or to step back even further, BCPL. It's a chunk of memory. And then the other bit that people talk about is this borrow checker, where we say, okay, this is where, you know, you've got a reference here, and the question is, what are these references allowed to be? And trying to explain that is what a lot of these capability models are all about, saying what is allowed to be referenced, what is not, what are you allowed to do given a particular reference, and they're all very detailed and they're all very low level. And then it introduces this idea of lifetimes. No time travel is one way to put it, and or in Rust speak, the target lifetime must enclose the source lifetime. Okay? And they also say no time travel, which means, I guess, most of the time, blah, blah, blah. Again, it's basically similar. You can't go back in time, but I'm afraid I have to ask you all to come back in time. To, in fact, 1998. Where a very clever chap called James Clark and David Clark and some Australians, well, one of them was a New Zealander, but enjoyed drinking, put this thing into Uppsala, and it's based on another paper which is possibly more readable for normal people, called Flexible Alias Protection and eCooper that year, and it said, look, if we want to keep all the promises that object orientation makes, particularly things about abstraction, about being able to think of an object only as an interface, and which protects its own implementation, so we can swap that or change it or rely on this encapsulation for security, then we need to make sure that some rules are obeyed. No incoming references is the big one. So you can't get into the inside of an object without going through the object that represents that object, and you know that you can't get to the object representing an object unless you have actually gone through the object which is representing the whole, the higher level of abstraction. Hopefully that makes sense. There will be arguments with a little less hand-waving shortly. Another way to think about it is that target object's owner must, if you've got a reference from a source to a target, the target object's owner must include the source owner. Enclose the source owner, sorry. There's the quote, which I'm not going to read because my time is running out, but you get diagrams like this. And, well, I'm going to declare that that's a tree, even if it's not. But this is actually from the Uppsala 98 paper. And the point here is that, you know, we have a root and we have a safe, I guess we have a safe object here, and in order for the ICFP people in the room to feel comfortable, we've used a couple of pairs here, rather than other things. So the point is, I guess, the safe object here owns these pairs, and what are you allowed or not allowed to do? Well, you're not allowed to do, for example, things like this, I guess. The dotted lines here are the ownership structures. So the root here isn't allowed to point to pair 2 because, why not? Presumably it's owned by this object, but this one here is owned, why has he done that? This one here is owned by the root, so the root is allowed to have access to the second in the pair. You can't see, oh, bugger, all right, sorry, I didn't realize, because it's behind me. So I guess the point is that these pairs can have references to their first and their seconds, And the dotted lines are ownership, so the left-hand pair is owned by that safe. The right-hand pair is owned by the root. The root is not able to get access straight through to the first pair, and this is what I realized. In spite of this paper being going on for 30 years old, it looks like there's a bug in the diagram. Cheers. I should try and do the Donald Knuth thing and offer you a check that you promise not to cash, because I don't actually have very much money if you find a bug in a diagram in a paper that I've built my career on, and other people have built their careers and languages. Well, I claim that anyway. Whatever. Right. I'll have to look at the paper again. Or somebody else. Could somebody else please actually check the paper? Do you see the problem I'm saying? The problem is that there's an X on that link B, which says the root object should not be able to point to the pair, but I'm arguing if those dotted lines mean ownership, it can point to that pair. Because that pair 2 is owned by the root, but its pair 1 is owned by the safe. And so the root would not be allowed to have a pointer to pair 1, but it would be allowed to have a pointer to pair 2. I've even given this talk before and I didn't fucking notice. Sorry, it means I'm going to. Right, object ownership, here we go. Here's another paper. Again, I love the sort of low-res quality you get from going to the ACMDL and grabbing the bits. Again, what this means is given some owner, we can talk about stuff that is, or an object which is we're thinking of an owner of a group of objects, or the inside of it, I guess. It divides things into the inside and the outside. And again, the rule is you can't have any incoming pointers. No incoming references. Like I said, the target owner must enclose the source owner. And crucially, a thing that's different from, well, again, on the object-oriented side, it's not, I was going to say for ownership, for flexible alias protection, but in fact, some precursor systems like islands and like capsules and various other things also behave in this way, which is there's no restriction on aliasing inside. There's no restriction on aliasing inside. So that owner could be a link object that represents a whole, a list object that represents a whole linked list. And D, E, and F could be the elements of the list. The thing that then flexible alias protection and ownership types extends that model with is the fact that F here can have a pointer to C. We can have outgoing references. So I can have a list, and I can keep the links in that list private, and I can alias them however they like, and then I can have links going out to other things, which is pretty cool. And you know, you can't necessarily do that easily in languages, some languages at least whose names begin with R, and possibly some whose names begin with O, and well, at least not yet anyway. Did I mention I was looking for a job? Right. Sorry. All the things I tell my PhD students not to do, I'm doing. Then, you know, we started to think, and again, work here done by Tobias and various other people, I think. The question is, okay, we've got these heaps, we've got these kind of heap structures. What can we do with the stack? And this, in some ways, is where the ownership and the regions work, or the OO side and the functional side, are coming back together again, I think. We knew about region types in the ML kit when we were doing the first work on ownership types. There are a couple of big differences, and the main one was we kind of assumed we were always fully garbage collected most of the time, and that meant we didn't impose any region nesting. Strong region nesting over the whole program in a way that, for example, the region calculus and the ML kit regions do. They're all very nested, whereas we were happy to say, well, we might have a garbage collector. So, you know, we might set up this deeply interlinked structure over here, and that might be interleaved through the execution of the program, and then that thing can go away, and it can go away irrespective of its temporal relationship with other regions that may have been created earlier and still be there, or may have been created afterwards and are still there. There's no global ordering. So, this is the next bit of the talk. Ownership, ownership, ownership. I've obviously moved things around. So, we're actually going sideways slightly. Here is another example. That's basically showing the same thing where I've drawn in purple links for the various ownership domains. You can see linked list, object. There's stuff inside the linked list, and then all of that might be contained in a wider context. Well, then what does this have to do with Rust, and what does this have to do with borrowing? Well, I wish I could skip this. Rust has this notion of copy and move semantics, and when I say Rust, I really mean it kind of comes from C++. I think it went from probably C++ to Rust and then back to C++ again. I can't remember the timing. C++ now also has, anyone know about C++ move semantics? That's kind of worrying. Don't tell the ICFP people because, well, don't tell the Rust people because they'd love to use a double ampersand if they could think of something for it. At some point I should write a paper called The Limits of Non-Alpha Numeric Characters in ASCII on Programming Language Design. How many different kind of things can we have when we express them with the syntax we've got in ASCII? So again, I'm just reusing slides, but I don't particularly want to. So Rust has this notion of a copy and a notion of a move. And it says in time that by default is move, which is actually a copy followed by possibly the compiler killing the source variable. Okay? And if you read the Rust book, it actually says the only difference between move semantics and copy semantics, which is why I really should have these slides around the other way, is whether you're allowed to access the source after the assignment. Under the hood, both a copy and a move can result in bits being copied in memory, where can means pretty much always will result in bits being copied in memory, or that might be optimized away. Okay, cheers. That slide was apparently so important that it's kind of there twice. Right, so now I really am slightly getting out of scope. I'm going to skip forward. What do we do about that? Well, yes, I am a serious computer scientist, really. I hope Brendan Eich didn't read this book before he designed JavaScript. I don't know that he did, but I don't know that he didn't. Anyway, this was a book done, again, about 25 years ago, talking about prototype-based programming languages. Self was just about to be kicked a touch or kicked in the head by Java, at which point almost all the Self group took what I call money from Sun Microsystems and then basically ported the ported the Self hotspot VM to something called Java Hotspot. And then most of them have now retired independently wealthy, except Urs, who apparently lives on an island somewhere off the coast of New Zealand that he owns and basically does Google, runs the advertising. He doesn't run the advertising company. He just keeps the advertising company running. He's chief CTO or something. Anyway, sorry. So I just put up that because that is Dolly the sheep, and there is Dolly the sheep. Doesn't have that much, well, in some sense it does have a bit to do with prototype-based programming because one of the ideas behind Self, and probably not the most important one, was, okay, we're going to make new objects not by appealing to a class, not by apostrophe, but by cloning, by getting an object and making a copy of it. And the problem with that is, if you know, and again, these terms are actually from Smalltalk, the problem is, well, how much do you copy? So if you make what's called a shallow clone, and most languages have this in, well, the catch is you probably won't copy enough. So if, in this case, I think that model's copying some kind of window, perhaps the red window, we're going to copy or making a green one, but it's sharing all the pre-existing resources that were already there. Things probably aren't going to work. On the other side, you can have a deep clone where, you can copy, sure, but you copy the entire world. How do you know where to stop? Well, you're going to copy the window, so you copy the window, and then you copy the window manager, and then you copy the underlying libraries, and then you just keep going. And I'm talking about it in kind of copying, but in fact, these problems arise in all kinds of areas where you actually want to do stuff with objects or with components or with whatever they are that are made up of other objects or components or whatever they are. Tobias gave a nice talk talking about possible Eka Python designs, or I think this is already there in JavaScript. If you're freezing an object to make it immutable so you don't have to copy it, you have the same problem. How do you know when to stop freezing? You might invite the little green men who are going to calcify your political system and agree that they can have Sevastopol, and then before you notice, well, the Donbass, whatever, they just keep going, they keep going. How do you know when to stop? Well, sheep clone is basically a clone which says, we will use the ownership information we have in those kind of trees that I've been displaying, the ownership trees, to delimit these sort of things. So what we clone is we will clone, if we say clone a window, the thing in the middle, we'll clone all the components that we know belong to the window, but we stop. You can rent Sevastopol, but you can't leave the borders of the municipality because that's owned by somebody else. And in computer programs, that means, you can copy the window and you will copy the window and you'll copy all the resources that are specific to that window, assuming the ownership's been set up properly, but then you won't decide you have to copy the whole system. The reason I'm mentioning that is because the work I've been doing is looking at building models of Rust and Rust-like things and ownership-like things to think about and saying, okay, well, how do we handle putting Rust's move and copy semantics into this James's sort of object ownership world? And part of what I'm saying is, well, this is how we would copy move and this is how we would copy move semantics and copy semantics. Sorry, what I mean. Yeah, I mean move and copy semantics. Right, I'm going to go back. So the interesting question then is, okay, we actually now have two independent hierarchies at this point. We have the ownership hierarchy, which is, again, type systems that people in this room have been working, oh God, for rather a long time on. The linked list owning its links, being able to have references outside. And then, again, whether in the name ownership or just stack-based allocation or stacks, you also have this other structure, which are the method calls. So in this case, maybe you want to enroll a student in a course, and to do that, you're going to call an insert method on the table, and to do that, you're going to go down and call an add method on the linked list. Okay, now the catch is, given what I've talked about no incoming references, this is a fairly subtle point that most of the models of ownership types so far basically kind of wave their hands when it comes to the stack. There are probably a few that don't, but most of them say stack is kind of a bit special. Maybe we will look back and see which object was the receiver in anyway. The problem is that, fine, your enrollment method, if it's got an object that's owning something, it could have a pointer to the course, but then there's this no oncoming pointers rule. So how the hell do you get inside the course? So the answer is, again, work done by some talented students and postdocs and people, and less talented people. There are versions of this that have multiple ownership. And the idea here is, okay, probably this was done slightly after the peak of aspect orientation when, having multiple dimensions of things or multiple aspects. I did hear people saying aspect in a tutorial on Sunday. Nobody in Uppsala land would have said that for 10 years. So it's nice to see it's coming back again. Multiple aspects here, you can say, well, these their tasks are owned by workers, but they're also owned by projects, and maybe that controls who can modify what. And there's been type systems done to model that. What I'm hoping, what I think can be done, is we can combine these two ideas. So basically, when you call enroll, you can think of the stack frame as being inside the course object. The stack frame for the enroll method, and that now means that's got to have multiple owners, because if you think about it, it's got to be owned by its calling stack frame, and it's also got to be owned by or have access to the inside of, which is another meaning of owned by in these systems. It's got to have access to the inside of the table. And then the table calls insert on the list, which it can do. It's got a capability. It's got a pointer to the list object. It calls insert. To do that, it needs to make a stack frame for that insert. Where does that stack frame have to go? Well, it has to be inside the stack frame for the enrollment method, because the enrollment method might have created some temporary objects, and it's got to be able to get access to it, so it's still got to have that relationship. But it's also now got to be inside the table object. And similarly, the table object can ask the list to add an object, and then in order to run that, we make a stack frame inside the list, and we run the add method inside that frame, and that frame is both, it's got to be inside the list so that it can access to the links and stuff, and it's got to be inside the insert because there may be stuff there. Thank you. I'm very nearly going to stop there, and it's kind of odd because the talk was called Against Borrowing. And I briefly talked about copy-move semantics, and I've talked about all those structures. And the slide I didn't get made was the one about borrowing. And in some ways, I'm going to say, do you know why? Well, obviously it's because, I'm ADHD and various other things and didn't really have my time management under control. But also it's because if there is a borrowing, it's actually kind of like that link there. Okay, that outgoing reference. The outgoing reference from the link to, well, it says bucket, I don't know, I think it was a hash table of students and grades or whatever. So an outgoing reference, that's a reference which points to something older than you, points to something higher up on the stack, okay? Those are what Rust calls borrows. You can't have a borrow that goes to an enclosing frame. You can't have a borrow that goes to something younger than you, right? The reason there are no slides is because I think borrowing is an epiphenomenon. Okay, I think borrowing is an I'm sorry if you... congratulations on the student, especially if you're in the room for doing a paper on the borrowing calculus. Congratulations, we do need that. We do need to understand precisely what on earth is going on at that really detailed level with the capability stuff. But remember the wood, the goblin wood, and remember that circle. Remember the goblin wood. If you take one thing away from this talk about why maybe thinking about borrowing is just kind of almost unnecessary, borrows are references, and they are references that are bound by the ownership of the thing that you are pointing at, which is I can probably go right back to the slide, which is pretty much a quote from the 88 Uppsala ownership types paper. It's an object can point to something that is inside the target's owner, and that, I think, I'm going to claim is the forest. That is the big picture. And I wonder if thinking more about that big picture means we will be able to do more things in our languages than we can. I'm not saying the little pictures aren't important, and I'm not saying it's not important to actually be able to explain what's going on at a very detailed level, the operational semantics and the capabilities and the possibilities there for optimization and eliminating these things, especially if you're eliminating... But don't lose sight of the forest for the details of the trees. Thank you very much.
Right, we can take questions while the next speaker is setting up.
I've scared everybody away.
So I think I fundamentally disagree that we want to always look at the forest. I very often want to look just at the tree, and I see borrowing as a mechanism to focus on exactly a tree. Now we can think that the borrowing is a reference, but we can also forget that reference exists altogether, and with the move semantics, I can just have the tree, work on the tree, and put the tree back in the forest. So why should I always have to care about the forest? Why can't we design programs so that we do not have to care about forests?
Well, I think the answer is it's nice, nice work if you can get it, and you can probably get it if you try. But unfortunately, there are structures where we do need to think about invariance of wider enclosing contexts. There are times when we do need to look at the larger structures. And if you talk about doing the move, if you say you just move in and out, that is basically value result semantics for passing procedure arguments. And there's a nice but very obscure paper by Henry Baker, read everything that he wrote in SIGPLAN notices, explaining why that's often not secure and will lead to differences in the semantics versus using references. I mean, in object-oriented terms, you might say, well, you lose object identity. Maybe you don't care, but you do. Jonathan.
Nice talk. I'm a fan of viewing the forest and have done it myself. At least tried to myself a few times. One of the concerns that I have is what are we trying to get out of ownership in Rust, right? And I think the key answer that people tell me is we're trying to get safe manual memory management, safe concurrency. And so the question is, can we get that with the forest, right? How do we reconcile this desire for a big picture view, but also more flexibility, of course, in our programming, which is, I think, the point, and also get those properties?
At that point, I'm going to say, well, you really should listen to Sasha. I'll check that the person talking was actually, whose name was on the thing, which I could read. Sasha's talk about a verified thread-safe array in Rust, because I think you can. And I think, I should stop quoting Shakespeare. You know, there are possibly more things in our philosophy of Horatio than we have thought of. One example would be, do you mind me mentioning cones? If you look at, for example, some of the stuff that Tobias and people are doing in Reggio, they are willing to have an object which is effectively an actor or a monitor for all its internal structures, right? And that's got some kind of lock on it, maybe a read-writer lock or maybe an exclusive lock. Once you do that, then again, on the concurrency side, you know, the topology of the references inside that thing, inside that bit of the forest, is irrelevant to what happens outside. Maybe. Then you've got the issue of the outgoing references, but you know, again, there are all sorts of options there. I'm not saying that you should necessarily just say, oh, well, we'll just go back to randomly writing pointers to everything and hoping. I'm not saying that. What I am saying is, I think that by improving, I don't even know if I want to say improving. I think there may be different trade-offs between conceptual models, between the way we think about our programs that underlie the languages we use to express our programs, that would be better places than the ones we're currently at, something like that.
Thanks.
That's all the time we have for questions. And like James said, Sasha is going to talk about verified thread-safe arrays in Rust with applications to things like video encoding and decoding. That sounds fun.
Hi, everybody. Hey. Yes, I'm going to talk about verified thread-safe array in Rust and how you can do that. So just for the context, I'm not trying to move the state of the art. I don't think so. But it's about application of the existing techniques in Rust, in the mainstream language, in industrial language. So if you have any applications, any possible use cases for where we can apply this technique, I would be really keen to hear about that. Maybe we can try to do another case study. Yeah, so just very tiny bit about Rust borrow checker. Rust is a programming language. It doesn't have a garbage collection, so it needs some kind of mechanism that statically ensures that memory is freed at the necessary point of time, that the aliases are controlled. So borrow checker is a static analysis phase that does that, basically. And of course, it has some limitations, and sometimes people face them. And one of them was faced by a group of people who tried to translate a media decoder from C to Rust. And in C, it's called David, the media decoder. In C, you can do implicit buffer sharing easily, right? You have buffer, array, you have two threads, you operate on the same buffer, nice, because you can pass the pointer to both of the threads. But in Rust, in safe Rust, you cannot do that. And there are different ways how to do that, or how at least to do simpler things than that. One of them is you can share the array in read-only mode. This way, you can just read from the array in 2 threads, 3 threads, whatever. Or you can split the array and get 2 non-intersecting mutable views over the array and then pass them to 2 different threads. This is also safe. Or you can go and use unsafe Rust, which temporarily switches off borrow checking for a specific code section of your program. But there you're on your own, okay? It's like C. Or the last option, of course, is mutex. Maybe there are other options, but the last on this slide is mutex. But in this case, you lose concurrency, you lose parallelism. So what David, media decoder, did is that they implemented their array wrapper in unsafe Rust. In debug, they do runtime index checks, runtime disjointness checks, that the writes and reads are not overlapping at the same indices. But in release mode, they don't do these checks. So this is a trade-off that they had to do for better performance. But at the same time, of course, in release, undefined behavior can happen, and data races can happen. And can we try to do both? Can we try to have both safety and performance? And one of the ways that I explored is formal verification. So one of the most popular verifiers at this point is Virus verification framework for Rust. It focuses on safe Rust, no unsafe Rust, as for now, but it has some special add-ons that extend the safe Rust and make it richer, and we are going to use these special extensions. So what's the API that we want? We want to create an array, we want to write to an array, and we want to read from an array. 3 simple operations, okay? And you can see, though, that the references here to the self object, to the array object, are shared. This means that you can pass array to multiple threads. If those are exclusive, then it wouldn't be possible. Now, the special extensions that we are going to use are called interior mutability in Rust. So in Rust, everything that is shared is by default immutable. You cannot write to it. But with Virus, there is an interior mutability thing, which is called permissioned cell. You can write, and it separates data from permissions. And now you can write to a data cell, even though you have a shared reference to it. This is how it works. So we will create an array of data elements, 2, 4, 3, 4, 2, 0, and we will have a map of permissions. And we have a main thread, and each permission at certain index, it points to each data element at the same index. Now we spawn the second thread, and we pass half of the permissions to the second thread. So now the second thread can operate on the second half of the data elements. The first thread can operate on the first half of the data elements. Secure. And this is, by the way, very high level. The details I can explain you after. But what we want is we want to have a map from indices to points 2, which is a permission object. And now we will propagate all of these permissions into each of the functions. So we will, instead of getting back the array when we want to create it, we will get back both the array and the set of permissions that corresponds to that array. Now, when we want to write to an array, we will require a mutable reference to the permissions map. And when we want to read it, we will require a shared reference to the permissions map. And of course, this also requires some preconditions to these functions, and namely, the permission set has to have the same ID as the array, so they have to be connected, right? You don't want to use some others permission sets for your array. Also, the permission set has to contain the permission for the ith element. So these are the preconditions. The good thing is that they are all ghost, so they are all erased at compile time. That's nice. And so let's do some evaluation. Media decoder is too ambitious. It's a big project. I'm a small person. So let's start simple. Let's do a parallel merge sort example. Everybody knows merge sort, pretty simple algorithm. The parallel version is also not that hard. This is the idea on how it works. So we have a first thread, then we split permissions in half. Then we spawn second thread, we do the same procedure. We split the halves of the permissions in half, into quarters. Now we have 4 sets of permissions. Now we do the same thing. Now we have 8 threads. And at this point, we can stop parallelizing, because let's say we have 8 threads in our system, 8 cores. So now we do just sequential sorting. And after that, after we sort it in all of the threads, then we merge. And merging is not shown on this slide. So if we want to compare our version of parallel merge sort with something, we want to know what to compare with. And a good thing that we could compare is the safe version of the parallel merge sort that uses split at primitive that I showed before, right? So it just splits and it does the index checks, the disjointness checks. No, okay, not the disjointness checks, but just every time you split an array, it checks that the split index is in between the start and the end of the current array, and then it gives you 2 slices. This is why it does all of number of threads split index checks, because we split only, let's say, 8 times or 64 times if you have 64 cores. And also it does many index checks when we write to an array or when we read from an array. But in the verified version, there are no index checks whatsoever. So that's cool. And we want to make sure we are at least as fast as the runtime checked version. We are the same, I should say. So we are 0.8% slower. A bit surprising. So what's the diagram about? 1.0 is the time taken by split at algorithm. So it's the baseline algorithm that we are comparing to, the runtime checked version. The virus is the verified version. And split at unchecked is the same algorithm as split at, but we use the unchecked versions. So they don't do index checks. And we see that whenever we don't do index checks and use the same implementation, we are slightly faster, 1 to 2 to 3% faster. But when we use our version, which is verified, we are mostly the same, and on average 0.8% slower. Why are we slower? So one thing that is important is that runtime checks are optimized away, okay? So if we try to interfere with array read-write optimizations, then it gets 30% slower or 40% slower. So even in runtime checked version, all of these checks or most of these checks are getting optimized away because merge sort is pretty simple. You split and then you iterate from 0 to n. So compiler knows that you're not going out of bounds. And the second set of reasons could be that, first of all, the implementation is different. Because in the first implementation, we have slices that recursively get split. But in the second version, we just have one pointer to the buffer. And it gets propagated to all of the threads. The second reason, the second difference is we use arc pointer, which is atomic reference counters. We have to use it because virus supports only standard thread spawning. But with standard thread spawning, we cannot use standard references. We can use only atomic reference counters. And the last one is some crazy, maybe unneat wrapper, which also is used by virus, which may or may not cause some slowdown. I have some slowdown experiments after, so we can discuss it later, but I just didn't fit them in the presentation. So what about the experience? Let's see whether users like it or not. So far, there has been only one user, that's me, and I will share my experience. We don't want it to look like this. What I liked is that I was pretty confident that my implementation is correct. My implementation is memory safe, because virus allows only safe code plus their add-ons, their interior mutability. But their interior mutability cannot compile if you are not using it incorrectly. So it might happen that my merge sort doesn't sort, that's possible. But it's not possible that it does it unsafely. So If it shuffles the bits around, it still does it memory safely. I don't prove functional correctness, but it doesn't matter what specification I give to my merge sort, it still will be memory safe. That's important. And for merge sort specifically, we can omit quantifiers because the splitting patterns is quite simple. You just split it in half, in half, in half, in half. You don't have to operate on sets of permissions because the slices, they are contiguous. So you can just operate on slices of permissions. This way you don't use quantifiers, and this way you don't use triggers and other things that come with them. But still, there are quite a lot of annotations. So there are 264 lines of code for the merge sort. Half of them is annotations, half of them is executable code. You might ask why there is any proof of memory safety if I said that memory safety does not depend on the specification and on the proof. Well, it's just because if I omit the specification, it won't compile. So I have to provide some annotations, and with them, it will compile. Otherwise, it won't infer what I want. Now, what could be improved? What could be improved is that verification frameworks can support mutable references in general, not just in some constrained positions in the first argument of the function, but in general. So you can return mutable references, you can pass them around, you can specify lifetime dependencies between them. So whatever Rust does with mutable references, it would be nice that verification frameworks would support them. Because with them, we wouldn't even have to introduce formal verification for merge. We wouldn't even have to use interior mutability for merge sort. We would just use split at unchecked and moved the index checks from runtime to preconditions. That's it. But because Virus doesn't support that, I couldn't implement it this way. And why atomic reference counter? So as I said, that there are two ways to spawn a thread in Rust. You can just send it and then join it yourself. Otherwise, it won't be joined. Or you can scope it. And this way, you are inside this environment which will terminate the thread. Doesn't matter whether you joined it or not. And in the second case, because Rust knows the statical scope of your thread, it can make sure that all of the data that has been pushed to the thread, that has been shared with the thread, it will be shared for a static amount of time. And once the thread terminates, then you can retrieve the data and you can regain the ownership of that data. But Virus doesn't support thread scope. This is why I had to use atomic reference counters. Yeah, but getting back to motivation, we started with media decoder. Media decoder, it could not use split at mute. It had some more complicated sharing patterns. Oh, by the way, I forgot to talk about it. Well, they had more complicated sharing patterns. They could not use split at mute, but merge sort, in merge sort, you can use all of the standard splitting patterns. So we want to have some studies which do more complicated sharing, more complicated concurrency. Could be David itself, but I'm happy to try other options. So if you have anything in mind, I would be down to try it on. One of them could be parallel shell sort. In shell sort, you sort subsequences of arrays in parallel, and these subsequences are not contiguous. So this could be a good example. But I have not tried this one on. But things, of course, they get more complicated with non-contiguous sharing patterns. So let's think. This is just a very recent slide. I just made it very recently. What could be the function for sharing permissions between two threads? We have an array, and we have permissions. And we want to split it in this fashion. We want this subset of permission and this subset of permission. And they are overlapping. No, they are not overlapping, but they are not contiguous. So in the preconditions, we say that, oh, P1 is disjoint with P2, and P1 and P2 are just mathematical sets. Permissions point to an array, to the array. We perform split, which is a ghost operation, just in compile time. And we get back the first set of permissions and the second set of permissions. And we make sure that both of them, they are defined by our mathematical sets of permissions that we provided. And then what else? And they both point to this array. This could be the function that people could use for arbitrary permission splitting, like a framework. And with this framework, I think people would have to prove two things. One thing is that indexes used in thread 1 belong to P1 mathematical set of indices. The same thing with the thread number 2. And this would be related to program verification, because we connect the mathematical indices that we have in mind, or actually in the program, but they are represented by ghost objects, and real indices. And we need to make sure that they are identical. But the last bit is the actual disjointness of these indices sets. And this is just mathematical, which is nice. But I have not tried to implement this function yet, so I'm about. Or if you want, you can do it. Thank you.
We'll take questions now.
Hi, this is a very nice talk, thanks. I guess I have a comment and a question. So one comment is, I think what you show at the end is exactly what you want, I totally agree. I think one way to look at this is if you could frame this in a program logic that can do this kind of reasoning, for example, in a separation logic. I think this kind of splitting is typically supported in the logic. I'd be super interested to chat about this. So we're keen to support mutable references in a much more general sense in the Prousty verifier very soon. So we could chat about this too if you're interested. I guess a question I have is, so at the beginning you explained what you can do in safe Rust or what your options are. I wonder if you see it this way, but it seems to me that although this is, I believe, exactly the right way to go about it, technically you're still using unsafe code, right? I mean, these functions are functions that if you were to call them in arbitrary ways, in particular, if you were to violate the preconditions, you could still cause undefined behavior.
Yes.
So technically, from the Rust standpoint, these are still unsafe functions. I really like this idea that, in a sense, they're less unsafe, right? Because you have the opportunity to use a verifier to guarantee that you're doing the right thing anyway.
Yeah, I agree. So in this case, the correctness depends on preconditions and postconditions. But what a slight advantage is that the verifier doesn't support unsafe Rust. So it's somewhere in between. We are using safe primitives from the point of view of the verifier. From the point of view of normal Rust, it's still unsafe. But we are not using, let's say, lambda Rust, which is about unsafe Rust.
Right. Okay. Thanks.
Thank you.
Great talk. I had a quick question about the performance stuff you were talking about. I know you said you could talk about it offline, but if you can say just quickly, if you were to manually go in and just delete all of the synchronized ref count operations on your arcs, what does that do to your performance?
Okay, thanks. Okay, so first of all, benchmarks were quite noisy. Yeah. I tried to see whether the noise is significant or not. So I tried to comparing the algorithm with itself, and the null hypothesis holds. So it still says that the algorithm, if you compare it to itself, then it's the same algorithm, which is good. It's just a preliminary thing. So then I tried to add arcs and remove arcs. Let's see. Yeah, so if I remove arcs, if I use thread scope, then I get a slowdown. Great. So I don't know. It's a future work.
Okay, and with that interesting...
and it's weird because in this case, so we take virus, we take our implementation, we ignore preconditions and postconditions, we remove atomic reference counters, we replace it with standard references, we get a slowdown. But if we take another implementation, which could be a raw mute pointer implementation, and we do the same procedure, so we try it with atomic reference counters and without, and the difference is marginal. It's just 3 milliseconds, so it's not even significant. So that's weird. So yeah, it's still future work.
Okay, and with that quite interesting result, we'll conclude, and let's thank the speaker again. And next, Yuan is going to talk about enriching resource reasoning for talking not just about safety, but also liveness. In particular, accounting for difficult features like diverging program executions. So take it away.
Okay. Yeah. Hello, everyone. I'm Yuan from Peking University, and I'm happy to share our work about temporal resource typing, which proposes a type-based solution for verifying liveness of resource usage. And this is in joint work with Taro Sakiyama from National Institute of Informatics. So first, let me introduce what resources are and what we mean by resource usage verification problem. So resources, they are different from other values in programs in that their states can evolve. So the valid operations that you can invoke on a resource can change. Examples such as files, logs, heap memory. So when you have a newly allocated heap memory, it is uninitialized, so you cannot read from it. And if it is deallocated, you can no longer access it. So the valid operations changes. We can specify this kind of usage protocols using we call temporal specifications to prescribe the usage traces. For example, the file usage here says that you should open the file first before it is read or write finitely many times, and eventually it must close. So we are specifying the full traces here. In this specification, we require the files to be eventually closed. And the log specification here says that acquire and release must come in pairs, and this usage pattern can repeat arbitrarily many times, including infinitely. So given these temporal specifications for each allocated resource, a program then is resource correct if during every execution, every allocated resource has a full usage trace, respects its assigned temporal specification. And now I want to show you some examples. So this is our first example, which is an infinitely running loop manipulating files. So in each of the recursive call, a file is created and opened, and its content is read, and then after some processing code, you close the file and continue with the next loop. So you can see this program first, it runs infinitely, which is typical of server programs or interactive applications. And second, every allocated file has a usage trace, which is simply open, read, close, satisfying the temporal specification for files. So this is a usage-correct program. And before presenting other invalid examples, I want first introduce the notion of safety and liveness because it appears in our title. So colloquially, we usually say safety is all about preventing bad things happen or nothing bad ever happens. And liveness is about eventually something good will happen. So consequently, there are two kinds of violations when we program with resources. The first kind of violation is that at some point, you invoke an invalid operation leading to a bad state, or more technically, you produce an irrecoverable bad prefix with respect to the file usage specification. And here, if you open the file and close it twice, it is a safety violation. And liveness violations are about, so for example, take the file specification as example. We have a desired event to be invoked, which is the close operation. So here I'm showing a usage that after opening the file, it is read infinitely. So it doesn't satisfy the desired closing operation. So in general, as you can see, safety can be detected by checking prefixes of usage only, but liveness, it cannot. For liveness, we have to reason about the full traces, especially when infinite executions can appear. This is more difficult. So after discussing these two kinds of violations, here's a simple safety violating one. So the same example program, but with close, move up. So you open the program and then close it immediately. But then if you want to read at this point, this is a safety violation, which leads to a bad state. So this is resource usage incorrect. And this infinitely running example here allocates a file at line 6 and then goes into an infinite loop. This loop reads the file in each recursion and continues infinitely. So it produces the trace we have just described, which is open and then read infinitely. Although, as we just say, so this usage trace is a safe trace because every prefix is good in the sense that you can just close in the next step to make it a valid usage. But actually, this desired close event is missing for the full trace. So this is a liveness violation. So now I hope before going to the motivation part, I hope that now you have a good feeling about what resource usage is and what we care about resource usage verification problem. And especially you've seen that for liveness, it is more difficult to verify than safety because it requires reasoning about full traces. So now let me motivate our specific interest in enforcing liveness of resource usage using types. So now let me first show you the landscape about type-based solutions for resource usage verification. So overall, I think in current literature, type-based approaches mostly focus on safety, but not liveness. So for these type systems, they apply invariant-based reasoning to prove type and resource safety. And second, they usually apply substructural typing techniques such as linear typing, ordered typing, or ownership types, using all these substructural typing techniques for strong update of resources states. So representative works here include type state systems and resource usage analysis and others. And so for liveness, we think there are few type systems for liveness of resource usage. And as explained earlier, I think part of the reason is that it requires reasoning about the full trace in infinite executions. So this is not entailed from type safety alone. So simply put, our goal is just to achieve a type system that enforces liveness of resource usage, which means we need to ensure not just valid or safe prefixes, but also valid full traces. So I'm repeating this phrase multiple times, I just realized. Okay, so our contributions are listed below. So first, we formally described what we mean by resource usage correctness. And I hope by giving these examples, you already have a good feeling about what we care about. And the second and the third bullet point is about our typing technique. And the fourth bullet point is about our proof technique, which requires a logical relation to capture the divergence happens when divergence happens. So today's talk will focus on the second bullet point, which I think is our main novelty, which is a resettable timer mechanism for ensuring liveness of resource usage. Okay, so to understand current work and our work better, let's first start by modeling temporal specifications as transition systems. So let's consider again this file example. We want this transition system to accept exactly the valid usage traces of files. So it specifies that a file starts from the initial state as init, and then you can open it to go to the second state, open state, and optionally you can read and write finitely many times, and finally you should call the close operation to go into the double circled accepting state, the closed state. So in this way, by modeling temporal specification as a transition system, a resource usage can be represented as transitions between the sequence of visited states. So, let's revisit the definition of safety and liveness again. So in this transition system view, safety is it is a local requirement that you should always take a valid transition in each state. On the other hand, liveness is a more global requirement, which requires the visited states eventually reach some accepting state. So here is a valid usage. So you open, read, close, so each of the transition is valid, so it is safe, and eventually you also goes into an accepting state. So this is a valid usage, satisfying both safety and liveness. And to understand current research on type-based resource usage verification, they usually follow these steps. The first step is that since we have this transition view of resource usage specifications, we can encode in the types of resources these resource usage states. So for example, let's consider type state systems. So the resource types carry directly the state of the resource. So a just open file has this file type with the type state of opened. And the second step is that for these resource operations, you need to update the type state in these types. So for an open event, it corresponds to the transition from init to opened. And lastly, for some strong update in the presence of aliasing, usually some substructural typing technique is applied. But that's mostly orthogonal to our research because we focus on liveness reasoning instead of supporting aliasing. So here, for simplicity, in this work, we just apply uniqueness typing, and you will not see any problem about aliasing in the rest of the talk. Okay, so in this way, let's see how our type system catches safety violations. And in this program, a file is created, same as before, and it is opened. So it goes from the initial state to the open state, and then it is closed, goes into the closed state. And at this stage, at this point, if you invoke the read operation, it is not it is rejected by the type system because the expected type is in the open state, but what we got is in closed state. So we correctly capture this safety violation. However, using this same infinite read example, we can see that liveness violation is not captured using this basic type system. So the file is opened and then goes into an infinite loop of read. So it stays in the open state forever and making self loops. So this usage is safe, but it violates liveness because the desired state close is never reached. So what should we do with this to catch this kind of liveness violations? What's the root cause of this liveness violation? So our observation is that the root of liveness violation is a lack of progressivity. So by progressivity, we mean that resources should reach the desired states, or in the transition system view, the accepting states, within bounded time steps. So in our infinite read example, although the execution continues infinitely by recursion, the resource, its usage state, is stuck in the second state, open state, and never make progress towards the desired state, the closed state. So conversely, let's consider a valid example with a progressive usage of files. So this example is slightly more complex. So this recursive function takes in 2 files, and the first one is assumed to be at open state, and the second one is a initialized file. And in line 2, we close the first file and open the second file, and we create a new file. Then we give the resource y as the first argument of the recursive call and pass the newly created z file as the second argument. So by applying some invariant-based reasoning, we can see that each allocated resource has this usage pattern of creation and then opened and then closed. And they are, this usage pattern happens within 2 recursive calls. So as demonstrated by the previous 2 examples, one invalid, one valid, we see that our core challenge is to ensure progressivity of resources using types. So our solution is to add a timer to the resource types, and its general form is of resource and has a subscript of its temporal specification and a superscript of its current timer. So when resources are created using the new construct, they are assigned a temporal specification as well as an initial timer. And our intuition for these timers is that they bound the number of recursive calls that a resource can be passed through. So this is manifested in our typing rule for recursive functions, which is a bit simplified version in the first order setting. So as you can see from the typing rule, when argument x is passed to the recursive function call, before evaluating the function body e, we will decrease all of the resource timers inside the argument. So the countdown operation is defined here. So it will structurally go inside the types to decrease all of the resources timers. And if the timer reaches 0 before if the timer reaches 0 before it goes into a desired state, then our type system will reject the program. Otherwise, if every resource reaches the desired state within a bounded number of recursive calls, this satisfies progressivity and hence Leibniz requirements. So this is our commented version or well-typed version of the, ill-typed version of our previous Leibniz violating example. Because no matter what initial timer you give to this file, it is not enough because infinite recursive chain happens. Therefore, the program must be rejected. And similarly, this is the valid example. And we have a usage pattern that each resource goes into the desired state within 2 recursive calls. So here I'm showing the evolution of the timers and the file usage states. So you can see when each recursive function application happens, the timer is decreased. And when each effectful operation is invoked, the state is updated. And finally, it goes into the closed state and ensure that the timers are always non-negative. So it looks good for finite usage, but how about valid infinite usage? So here's an example. We are programming with a single lock here. So we newly allocated a lock and goes into an infinite loop, which acquire and release this lock in pairs. And you can see same as the previous violating example. No matter what initial timer we give to this lock, it is not enough. So the problem is that we need a way to reset the timers. So this is exactly what we do. We add a ghost construct reset to the language. And it allows resetting the timer of a resource whenever the resource is currently in a desired state. So this way, valid infinite usage pattern can continue infinitely by resetting the timer each time it is currently in the desired state. So this is the same example, lock example as in the previous page, but I added the reset at line 5, so it goes smoothly. So here is something about the actual representation of temporal specifications in our formalization. So each temporal specification, as you see, resources can be used in a finite usage or using it infinitely. So we have two components. The left one is a set of finite traces prescribing the valid finite usage of a resource. And the second one prescribes the valid infinite usage patterns of the resource. And the infinite specifications is a finite set of what we call lassos. So it is making an analogy similar to the automata theory. So each lasso has an initial component S1 and a repeating component S2, and it prescribes a valid infinite usage pattern by producing some trace in the initial part and then repeating by producing some trace in the repeating part. So this is a general representation that incorporates both omega regular expressions or omega context-free grammars. And a resource is considered to be in the accepting state or desired state if its finite specification is satisfied or it finishes producing some initial finite trace in a lasso and is ready for the next repeating pattern. So yeah, I think that's all about my talk, and I'm happy to take any questions.
Hi, great talk. I had one question that your system support dependent typing such that it would be possible to pass a open file handle to a recursive function multiple times, but the recursive function is like bounded by a few.
Yeah, thank you. I have a backup slide for that. So as you can see, one of our future work is to support value dependency in timers. So when you have a recursive call that is not bounded by a concrete natural number, you have to use some kind of value dependency to support, to type check the program. So here is some example that we think could be type checked if we have value dependency, because here the round robin scheduler, each resource, before it is scheduled, it is how long it needs to wait depends on the current length of the active list or the wait list. So it requires value dependency. But yeah, we think that's possible and shouldn't be too hard. And this is left for future work.
I find this quite hard because you said the timer must be above 0.
Yep.
That means that you have to reason about whether values in the programs are above 0.
Yeah. So some kind of constraint solving is required.
Yeah, sure. Thank you.
All right, let's thank the speaker again, unless there's more questions. started. Paulette is going to is going to give an extended version of her very recent ICFP talk, as in literally last session, but from a memory management, but from a more IWACO perspective. So let's take it away.
Oh, okay. Yes, thank you. Yes, I'm slightly out of it. I just gave my ICFP talk. For those of you who were there, I apologize. There might be some repeating ideas, but try to make it more approachable for this audience here. Like Matt mentioned, this is my ICFP paper, but I'm kind of more focusing on, there's like, I don't know, maybe like a page of future work. So now I'm taking that page of future work and trying to extend it further to a talk. So it feels like there's been kind of a resurgence. I don't know if you all know this in the workshop of like region-based memory management. Seems like it's kind of hot these days. I wonder why. Oh, I know. Yeah, so there's this recent paper talking about reference capabilities for flexible memory management, where we can sort of make a whole forest of regions and interact between regions in this really nice way. And with beautiful visuals like this. I love these visuals, and they're little bean-shaped regions. There was even a paper that came out this year at I believe ICFP. This Spigen work talking about implicit and non-lexical regions with size allocations. And then there's, of course, always new work on reasoning about aliasing. So, recently reachability types and all this. And so I'm a theoretician. So, when I read these papers, my first thought is, I might read the intro, some of the related work, get some of the context, and then I want to look at the details, right? And when I look at the details, I'm like, whoa, what is going on here? What are the models for these languages like? And so really a lot of these works are all kind of built on higher order state, right? So we have really great languages for reasoning about aliasing and ownership and all of that, and that's all kind of related or maybe sort of built on, reasoning about regions and static memory management, which is all built on this idea of higher order state. And I kind of live at the very bottom of this. So this is where this talk is really, and this paper is really about reasoning about higher order states. And really I'm thinking about a new model for higher order state. And in particular, in this paper, we talk about how type universes can create a simple model of higher order state. Now, I really don't like the word simple. That seems to carry a lot of weight and doesn't really say anything. By simple, I really mean, there's no step indexing, no later modalities, and continuous spaces. And so, by starting on this kind of simple model, the hope is that we can extend the simple model, hopefully to these other, so back here, these other kinds of languages with all kinds of complicated reasoning principles, and hopefully we can extend it towards reasoning about models for those languages, right? So not all of you might know what type universes are, so let's talk about that. So type universes come from dependent type theories. So in dependent type theories, we not only like reasoning about terms and their types, but we like reasoning about types themselves and of type, right? So you might describe the identity function as taking in any arbitrary type, and given an element of that type, we'll return that same element, right? And you might think, well, of course, I should be able to apply the identity function to itself, right? And I'll just get a function back. But then you think, well, what's the type of this function that quantifies over all possible types? And this turns out to be, an inconsistency, kind of related to Girard's paradox, right? And so what dependent type theories do instead is that we kind of stratify the types and we say, actually, I'm going to quantify over all types of a particular level. And my types that quantify over all these types at a level are going to live in one type level higher. So this is type universe hierarchy. And so you can kind of visualize it like this. We have a type universe hierarchy. Type 0 is contained in type 1, which is contained in type 2. And in our ICFP paper, we kind of found an interesting correspondence with these type universe levels to levels of the heap. So we have heap 0, heap 1, heap 2, but how are these levels actually formed? They're formed by references, right? So references to values in heap level 0 are going to live in heap level 1, and then references to heap level 1 and heap level 2. And in our paper, we actually prevent references cross-cutting across levels. So in particular, we prevent heap 1 to heap 2 references and self-references. And we do this by imposing a kinding system on our language. So the kinding system, again, the way that we get these different levels is we have kinds for any particular type at any level. A reference to that type is going to live in a level higher. And then we also have to classify functions along this type universe hierarchy. And this ends up simplifying the model quite a bit, these restrictions that we impose on these references, right? So for a model of higher order state, we run into something called the type world circularity, where we're trying to define our world, the model of the heap, sort of in terms of itself, right? And so we need to impose, past models have sort of imposed some sort of structure on this by like step indexing or later modalities or something else, or using recursive domain equations, right? But instead we've just stratified our types, and we get a nice correspondence from the stratified types to our stratified worlds, and we don't encounter this type world circularity. So we get a very simple model. Another benefit is that for these particular programs that deal with higher order state, we get termination. And so for a subset of a language, if you know that you use these kinds of references, you know you will always get a value back. And this gives you very strong reasoning principles for that subset of the language. So that's quite nice. And so then I've kind of vaguely pointed at type universe hierarchy. Here's kind of it more concretely. We have this type universe hierarchy where the base types, sort of like nat to nat functions at level 0 and bool are going to live in type 0. And references to natural numbers are going to live in type 1, and we kind of climb the hierarchy from there. And we can then, if we look at values that inhabit those types, we start to see the stratified heap. So heap 0 is, kind of our base values, and then we have references living in heap 1, heap 2, etc. But these are all just pretty pictures, right? So like, how do I actually know that my values obey this stratification that I've just drawn up here, right? And for that, we have to look from fancy pictures to fancy calligraphy. We got to look at our model. And so basically what I'm trying to describe here is the semantic values of a particular type tau. And you can kind of think of it as a function from types to semantic values, right? But this function takes 2 extra arguments. It takes the type level of a particular type tau, and also takes our model of the heap, the world, right? And in our model, when we're trying to get the semantic values of a particular type tau, we actually restrict the world to its type level. So it's literally inaccessible to any other parts of the heap. You can kind of also think of it as almost garbage collecting part of the heap. So if we're thinking about the semantic values that live at level 1, we garbage collect every level higher than 1, and so we know those values can literally not access any levels higher than heap level 1. So this is pretty interesting, and we might think, well, why are we considering these as levels? What about thinking about these as regions, right? So we say each of these type levels is a region. But you might have this intuition already. It turns out these type universes are actually huge in the number of values that they store. So this is not great for region-based memory management. I mean, basically all of our basic values live in, type level 0, so we'll just never garbage collect those, which seems really bad for memory management, not desirable. And so looking at a particular type universes and the values that inhabit the types that live in those universes, we kind of have to think about, okay, is there a way to start grabbing values out of there and allocating them somewhere else so that we can start getting smaller regions and get the benefits of small regions for static memory management? So could we just like grab this identity function out of the type 0 and say, I want to allocate it in some type universe beta, and then once I no longer have a reference to type universe beta, I can then garbage collect it, right? And this has a kind of interesting correspondence to something that exists in the dependent type theory work, which is type universe polymorphism. So I'll talk briefly about that. So revisiting our identity function from before, we're quantifying over all possible types, type 0 here, and we know that that type gives us type 1. But if we want the identity function to work over type 1 level types, well then we kind of have to redefine the identity function for type 1 level types, and then we have to redefine it for type 2 level types, and so on. And this is quite annoying. So people came up with polymorphism. So here instead we could say give T the type, the polymorphic type level I, and then for any type level I, then this function type is at type I plus 1. And there's been some recent work doing universe polymorphism by displacement. So the way that you would actually implement terms at particular different universe levels is by using a displacement operator. It works over the term and the type. So for any term at a particular type, we can displace it to a different level using this displacement operator. And how this works over types is that for a type that might be considered at a different type level, we can use the displacement operator to put it into a universe alpha plus beta. And so if we think about coming back to our universes, we can kind of imagine that we can use this displacement operator to displace this identity function or any kind of value into a different type universe. And then whenever we're done using that type universe, then we can garbage collect. And we can sort of view this as almost a forest of regions. So anytime we want a value, we want to allocate it into some sort of different type universe or really region, we can do that. And then as we see that those regions disappear, we can start garbage collecting them as we want. And so if we kind of revisit some of the work that's recently been happening, you can kind of imagine like a syntax for this language might look like, I don't know, it's slightly similar to this one. So in this one, we create a new region R. It's going to have the 2 there for the size, because they cared about sized allocations in this work. But you can imagine that like we could have a similar, like a displacement, allocate this pair of 2 references into the region R. But one question they might be having is, why are these stacks, right? Like each of these regions are stacks based on references, right? So a reference to type beta is going to live in this next type beta plus 1, and so on. Why can't we just start having arbitrary kind of relationships between all these type universes? And so you could kind of, so here we kind of have like one of these regions is kind of following the stratified discipline, but one of them has actually a reference living inside of the region, and one of them just is one reference to type alpha plus 1 in a completely different region, type gamma. And so you can kind of imagine like in code, we could kind of start imposing constraints over our universes or our regions, right? So you could say, for this particular shape that I want to create, I could say each universe is kind of distinct. References, to beta stay within type beta, and then like references to alpha plus 1 are in this other disjoint type universe. And there are some languages that use constraints between universe levels, some dependently typed languages like Rock, for example. So again, this is sort of taking work that is done in dependent type theory and trying to see how it applies in our space with reasoning about memory. And so what we found in our work is that there's kind of almost like an algebra of levels that we have. So we have these levels that correspond to, in the semantics, the values, what parts of the heap that the values rely on. And then there's sort of a relation between a reference and what it stores. And there's a relation for a function's type level if you want to start reasoning about higher order state. And you can sort of start tweaking all these levels and the relationships to try to get more interesting combinations of these type universes. Okay, so to summarize quickly, I'm a theoretician, so again, just a reminder, these are all just like very abstract ideas that I have, and I would love to discuss it with all of you who are experts in this area. And I kind of found an interesting model for a higher order state and some connection to existing work in type universe hierarchies. And maybe there's a connection to sort of start expanding this model to start modeling languages that we already have, right, that do really interesting and useful things with region-based static memory management. And actually, there's conditional accept at Popple. There's this type system for disentanglement, actually. But interestingly, they have this invariant, they call it up pointer invariant, and sort of like they have these timestamps on references and types. And I actually think that this like timestamp kind of type system, there's also like potentially some correspondence to universes, and maybe this universe, this model with using type universes could also model languages like this. So it's a very exciting space to be in. Okay, so just to summarize, we used a type universe hierarchy to reason about the heap. It's kind of weird. Maybe there's some usefulness here, maybe not. But I would love to try and start reasoning about languages that have much more sophisticated reasoning principles about memory, and see if any of our models can sort of extend to those as well. Thank you very much. I gave my ICFP talk earlier just specifically about the paper, but I kind of covered it here as well. And then a bunch of people from my group are also giving talks, so go check them out. Thank you very much.
Yeah, thank you for a really clear and easy to follow talk on work that seems really elegant and really deep. A couple of questions. One is, I notice you've got your red forbidding references from one universe to another universe. Is that intrinsic to the system, or you could basically, you'll lose some guarantees, but is that required, or you could basically let that one go if you needed to?
Yeah, so like because of this algebra, you could kind of say, oh, actually I don't care about the relationship between references. I don't want them to actually bump the level, and then you could kind of have unrestricted references at that point.
Or at least restricted by what other constraints you have between the type universes.
Yeah, exactly.
So you've got full, can the type universes be partial orders rather than, if that's the right word?
Yeah, so I kind of like...
you did hint towards that.
Yeah, so this kind of like stacks in this like forest of regions was a little bit of a lie, like because the displacement is really displacing according to some like partial order. So instead of actually...
you're going to want a partial order.
Yeah.
So I think.
Yeah.
And I'm going to have to go to other talks, unfortunately.
Oh, okay.
But there's the joke question, which how are type universes related to universe types? You don't have to answer, it's just a joke.
Yes. But we talked about that in the paper, though, so because we did get that comment.
Anyway,
yes.
Thanks again. I'm sorry I have to dash. I'll be back later.
Yeah. Thank you.
Hi. Thanks for the talk. Very nice talk.
Thank you.
Yeah, you didn't mention type and effect systems for region-based memory management, right? So I think there's a bit of a difference between what you presented and that other work, because in that other work you can have references that point to the same or to previous regions,
right,
as long as you are not using them, and that's where the effect system comes into play.
Right.
Is there a way to kind of get the same thing, maybe with something like gradient monodes or something like that?
Yeah, I do feel like there's probably a way to do that, but it might need to, like, you might have to start bringing in like linearity, because there is like some linearity constraints, right? When like, certain regions can be opened, but no other ones can be opened, and things like that. And so you probably need more constraints than what I've kind of thought about here.
Okay, thanks.
Yeah, thank you.
Really fun. This is a lovely talk. One of the things that we do a bunch in code written using my version of this many systems you've been alluding to is we wind up inverting a relationship where something originally pointed to dominated owns something else, and then later it'll swap.
Mm-hmm.
Is that something we can do here, or will that require some extended modeling that makes it less elegant?
Yeah, I mean, I'm assuming, it would be really interesting to see if that would work. I have like no concept of how this might work, but I would love to talk to you to talk about like in sort of more realistic languages, what kinds of like memory operations do we want to perform, and then start thinking about, okay, how do we model that? Can it still be used in this kind of system? Yeah, that'd be great.
Fun.
Okay, if that's all the questions we have, or maybe there was one over there.
This was great. I think I don't quite follow in the hierarchy and sort of making sure that you're sort of chaining your references in an appropriate way. I don't follow in what is displayed here, the type beta where you have S referencing within the same type level. Yeah. So actually, I didn't cover this in either of my talks, actually. There's not enough time.
But there's actually an interesting, another type universe hierarchy you can have is that there's like a base universe in which you can quantify over everything in that base universe, and then the rest have to be stratified. And so there's kind of an interesting correspondence in our paper that we can still have this behavior of like, within a certain type universe, we can have references to live in that same type universe, but as long as the other universes are stratified based on functions, then we still maintain termination. And so this sort of relationship already exists. You can kind of say, oh, references to type beta will just stay in type beta, and so they kind of exist in the same region. Does that help a little bit? Okay.
Just a question, just to follow up on that thing. The separation between the need for termination and being able to deal with dynamic data structures like trees, lists, and so on. I was just wondering whether you really want to make sure that you cannot have these kind of data structures. You would like to have those in regions as well.
Yeah.
Right. And maybe not. Maybe you want to give up termination.
Yes. Yeah. Absolutely. Yeah. So I think this is just like as a basis of like modeling languages that already don't have termination, but then we can sort of use this model to start reasoning about these languages, maybe prove more equivalences, be able to optimize these. But yeah, we would eventually clearly give up termination because it's quite restrictive.
Okay, seems like that's all the questions we have. Let's give the speaker another hand. And our next talk is some work that I happen to know quite well. I worked on it as an undergrad, and my now advisor is going to give you all an overview.
Super, thank you. This is a talk on gradual verification and how we're building this new kind of verification system to assure software incrementally. This was work led by my graduate student, now graduated, Jenna DiVincenzo. She's a assistant professor at Purdue now, but also a large team of other people, including Hemant, as he mentioned. Today, since this is IWACO, I'll be talking about the particular role that ownership plays in this system. Let me start by motivating this by the problem of verification. Let's say we want to specify some kind of system here. This is Daisy, the programmer, and she wants to verify that findMax actually returns the maximum of a list. And so she writes an insurance clause that says the result is the maximum of the list, and meaning it's greater than or equal to every element, and also that the list contains that, right? So we don't just pick some arbitrarily high number. And so this ensures clause turns into essentially assertion at the end of the function. And we could check this with dynamic verification, which checks it for every run. But of course, we might want to make sure that this holds for all possible runs. And of course, the cost of dynamic checking might be significant, right? In these two functions, you might imagine might traverse the list, and so we would incur kind of an O of n overhead on checking, not even beyond what it takes to implement the function. So we could apply static verification instead. But of course, unfortunately, it's a little bit naive to expect that most static verifiers would just be able to verify an assertion like this, because we do this and we get a bunch of warnings, and it's sort of reasonable that we would get those warnings because actually we have to put it in a precondition, right? This code won't work unless the input list is not null. And in fact, for most verifiers to prove software that's sort of interesting, maybe a little more interesting than this, they probably require some help, right, in the form of loop invariants and maybe some lemma functions, some folds and unfolds, which I'll talk about. and so there's a lot more work for DAISY to do in order to prove this correct with static verification. What we're going to do instead is try a technique called gradual verification. And gradual verification is going to allow us to leave out specifications, and we'll check them statically. We'll check the specifications we do put in statically wherever possible and dynamically otherwise. So now, actually, our original specification is sufficient. If we leave out the requires, that just means requires question mark. And what question mark means is this is a specification we have not given yet. It's unknown. And so the gradual verifier, it still can't check much statically, right? But it will at least provide dynamic feedback, right, by doing dynamic checking in this form. Now we could then extend the specification with more and more clauses, right, to more and more information. So we could say, yes, actually, I know that the input list is not null. That might be important. And as we do this, then more of and we could add some loop invariants. Eventually, we could add the folds and unfolds and lemmas. As we add each piece, we get more and more static verification until when we have the entire thing specified, we have a fully static proof. But DAISY can stop at any point, right, when she believes she has achieved high enough assurance. Just as an example, this is, of course, a trivial example, but most of the verification conditions from this code can be statically verified with only half of the lines of specification code that we would need to verify all of them. Basically, there's a lemma at the end that is a lot of specification, right, that fills things in. So you can get quite far towards assurance, at least in this notion of percentage of verification conditions checked statically, with perhaps a minority of the annotations that you would need to check everything, which is, potentially quite nice. And in fact, you can get into memory safety already after just 13 lines of specification, about 40% of the work. Everything except the lemmas is 86% right, and then the full spec is 100%. So to summarize, the problem that's motivating this work is that dynamic verification is low cost to the programmer, but we don't get any feedback at compile time, and we don't get any static guarantees, and of course it can slow down the program, sometimes a lot. On the other hand, static verification pays off only after a ton of work, right? Static verification can be 10 times as costly as writing the program. We have data on this from SEL4 and CompCert. And it requires basically an inductively complete specification, right? If the spec is incomplete, you'll get a warning, right, saying that you have to specify more things. It's kind of viral, right? And the same, if you think C++ const is viral, try Daphne, right? You might even think of these as false positives, right? It's not that your spec is incorrect, you just haven't proved it yet, right? And so with static verification, you don't get any feedback on incorrect specifications unless there's a static inconsistency. So what we'd like to do is get more incremental payoff for incremental specification work and the ability to focus on the most important properties of the most important components first. And gradual verification is going to give us the ability to do that, much as gradual typing allows us to say, oh, in a dynamically typed language, let me add some types to the components that I care the most about, right? And our work is directly motivated by research in gradual typing. And so we want to provide early feedback on mistakes, both compile time based on the specs you've put in, and runtime, because we can run incomplete specifications. We'll check any specifications that aren't checked statically and give you feedback on them immediately, right? So in some ways that might be earlier than static checking, right? Which might not tell you about those things. Finally, we have some nice properties. I'll talk about these in the next slide. There's a property of soundness, which says all specification violations are caught either statically or at runtime. There's conservative extension. So if a specification has no question marks and it verifies, then the code is correct, right? And that's a static notion of soundness. The gradual guarantee, right, which is a standard property of many well-designed gradual type systems. If your specs are a subset of a correct spec, that is, if you're sort of on the way but you haven't gotten there, you won't get any errors either statically or at runtime. And then finally, pay as you go, right? This one's a little harder to verify analytically, at least in our case, but the idea is that hopefully the runtime checking cost, well, it'll first probably increase as you add specifications because you have to check those specifications, but eventually it decreases as those specs become statically verifiable. And we have some evidence for this, which is in a Toplas paper from earlier this year. I need to update the slide with that citation, actually. I won't talk about that today because I just have a short slide here. Let's talk a little bit about, though, how gradual verification works. And I'll start actually with ownership. So why is ownership important to verification? This is maybe preaching to the crowd for some of the IWACO old-timers, but maybe there's some people who haven't seen ownership all that much before. So let's look at a very simple property of a simple system. Here we have a counter. It has a field x, and we're passing it to an increment count. And I might write, actually, in our gradual verification system, we can write a spec that says, hey, coming in x count is n, and coming out x count should be n plus 1, right? And maybe some other things that I've left out with a question mark. Now, if we know that x count is 0 and we increment the count and pass x, then we know that x count is 1. But let's say y count was in scope. It used to be 0. Is it still 0, right? Well, I don't know. It seems like it should be 0 because I incremented x and I didn't increment y. But of course, if x and y point to the same counter, right, the same object in Java or in C, then y's count will have been incremented. It will now be 1, right? So we don't know. And this is actually a problem that stymied verification for maybe 3 decades. And the solution was separation logic, and we're using a variant of separation logic here, which builds ownership into the logic. So this is about ownership. So the rule is that you can't change the fields of an object. In fact, you can't even reference or talk about the fields of an object unless you own those fields. So how do we express ownership? There's this access predicate, access of x arrow count. So this idea comes from the idea of implicit dynamic frames. And access of x dot count says I own the field x arrow count. And so to even talk about x arrow count equals n, we have to have access to x arrow count, okay? And then, of course, we want to return ownership to the caller, so we'll also put access of x arrow count in our ensures clause. And so now, if we know that we have x and y, then we can say, well, I access x arrow count, and x arrow count is 0, and I access y arrow count, and y count is 0. How does this help me? Well, the other part that comes from separation logic is this special kind of conjunction, right? Separating conjunction star that says if there's an access on 2 different sides of a star, then those must be 2 disjoint fields in the heap, right? And so we know x and y cannot alias because their count fields are different, like different pieces of memory. And so what that means is when we call increment count on x, we'll just pass the access to the x. We'll keep the access to the y. We know they're distinct, and so we know that y's count is 0 at the end, okay? So that's why ownership is critical to verification. It allows us to talk about, what parts of the heap might be changed by a given function, increment count in this case, okay? And if you're wondering, this spec is actually okay because question mark can include access to x arrow count, right? It's incomplete, and the complete version includes access of x dot count. Let me talk about an example that gets a little bit more interesting and also includes ownership. So here I have a predicate that says a list is acyclic. And the idea is that I have an acyclic list, and then I I might add a node to the front of it, and then I'd like to assert that the list is acyclic again. So what does acyclic look like? Well, we define a predicate that operates on the root of an acyclic list, and the predicate tests whether the root is null. If the root is null, then we're fine, right? An empty list is acyclic. Otherwise, we assert ownership of the value and next fields of the first element of the list, the root of the list, and we assert that the rest of the list, acyclic, is root arrow next, right? And so we have these accessibility predicates again, permission to access those heap locations, again, ownership, just in logical form. We have the separating conjunction that says these fields are all different, and importantly, the access to this first node in the linked list is separate from the acyclic of the rest of the list, right? And so that's how we know the list is acyclic, right? The first node is different from all the rest, and that's the rest is acyclic too, and so iteratively you get that the whole thing is acyclic. Okay, so that's that specification. Now we can see how we use it, right? So let's say Daisy is writing this list insertion program. She starts out with an acyclic list. When she allocates a node, then we learn since this allocation succeeded. If it didn't, we'd have gotten an exception and we wouldn't be here. So we know that L is not null, and we own L's value in next fields. L.next is the old L, right? And so that's still acyclic, right? Because we didn't change that at all. So now if we look at this predicate, we see that the thing we know about L is exactly what we need to know to show that L is acyclic. And so we can do what's called a fold operation, which takes basically the pieces of an acyclic definition, the right-hand side, and folds it into an acyclic predicate. And now we can say, okay, I have an acyclic list, happens to be one element longer. I didn't specify that. I could by putting like an index on the acyclic predicate if I wanted to. So that's how we prove this code statically. But we could also make it gradual, right? So if Daisy didn't specify that the input list was acyclic, she could have just written a question mark. And then we allocate a new node. We know that it's that we own the heap portions for that new node, and that it's not null. And we also, retain some unknown information that we had before this allocation. Let's say we want to fold the acyclic code again. Well, we have part of this information, right? We have that we own access L-val and L-next, and that L is not equal to null. So we're in that second case of the acyclic predicate, but we don't have acyclic of L-next, right? And so, but the nice thing is that we can get that from the question mark, right? So the static prover is going to optimistically assume that we know acyclic of L.next, so we can do this fold successfully and finish our code, right? And then what's going to happen is later on we're going to fix things up by checking dynamically that this missing piece is actually true at runtime, right? So we will eventually check this soundly, but it'll be a combination of the static and dynamic checks. Okay, so one thing that's interesting about this, because we're trying to do dynamic checking, is we have to ensure all specifications are executable. And one of the most interesting bits of that is actually the ownership, right? So one of the things we do is we check that we can assert access of x.f. How do we check that? Well, we need a list of what the currently executing method owns, right? And so that's basically, there's a set of object field pairs. When we assert access of x.f, we verify, do we actually own this field? Anytime we assert a separating conjunction and we want to check that at runtime, well, we have to basically see, do we own all the things over here? Do we own all the things over here? And do they overlap, right? If they overlap, that's also will be an error. There's some other details, disjunction. We have a special form of disjunction. Well, we use if instead of disjunction because it makes things more kind of, they're easier to check. We could check disjunction too, but it turns out we get exponential checking in the presence of ownership. So that becomes pretty important to like know which branch of a conditional you're in. And this is usually not like a big burden. A lot of static provers also use if instead of disjunction in their proof language. Another thing that's interesting and also interacts with ownership is recursive predicates. So like this acyc predicate, if we assert that, how do we check it? Well, basically, the acyclic predicate is a recursive predicate, and so we can turn it into a recursive function that just kind of goes inside until we get to the end of the list and checks that we own things all the way, right? Now, what's interesting is it would be kind of bad if we asserted something at runtime and it didn't terminate, right? Because our program would then like stop while we were doing a runtime check. There's a nice, elegant solution there, which actually came to us from ownership. So in our system, when you define a abstract predicate, in any recursive case of that predicate, you have to assert the ownership of at least one heap cell. And if you think about it, that means every time you unfold the predicate dynamically, you're eating up one more cell of the heap, and eventually you get all of them, right? The heap is finite. So you might wait a long time, right? If you're traversing the whole, if your linked list is like using all the memory on your machine, it'll take a long time. But every time you go through that linked list, you'll assert the ownership of a new cell, and eventually you'll get to the last one. So that's kind of a fun trick. I guess I have some slides on producing the dynamic checks, but I kind of talked about that, right? This is the part we know statically. We're trying to get acyclic, and so we do what's called, we do a dynamic check on the acyclic of L not next. There's an interesting theory issue here, which is that our dynamic checks are what's called equirecursive. We basically treat the predicate as equivalent to its unfolding, whereas what we get in what we have in the static world is isorecursive, where you have to explicitly kind of fold and unfold to look at the inside of the predicate and then look at the outside of the predicate. And so some of the interesting theory in this system was actually getting those to match up, making sure they did match up in our system. Let me talk a little bit about the last technical topic here, a little bit about how we dynamically verify ownership. So like I said, we have an ownership set, and let's say we have a couple of lists, X and Y, in main. And we'll keep track of, that main owns all the cells of X, those are the green cells, and all the cells in Y. And let's say these are acyclic and separated. Now, we call a length function. Requires acyclic of X, right? And so our stack above main, we have length. And what does length own? Well, we passed acyclic of X into it. And so our runtime system is going to actually, kind of enumerate all those things that are in X and pass their ownership to length, right? Because main still owns Y, we want to make sure that length, can't change it. In this case, length is probably just computing the length, so that's fine, but it could be ill-behaved, so our runtime system will make sure it works. On the other hand, if length has a question mark as predicate, then that means, maybe it accesses X, maybe it accesses Y. We don't know what the spec is. So we don't want things to fail because we haven't specified the spec. And so we optimistically pass the ownership of everything to length in that case. Okay, so it's kind of an interesting approach to get this gradual guarantee, right? That code will not break unless we have kind of a proof that there's a problem with it. This actually leads to a very interesting application, which I haven't seen in other work on ownership. Let's say you want to restrict the ownership of some code, right? So here, back to my counter example. Let's say I have I have restrict ownership. From main, I create two counters and I call restrict ownership. And restrict ownership just takes ownership of X, right? And X is, let's say X is different from Y. Now I call do compute. Do compute is completely unspecified, right? I have question mark in requires and ensures. Maybe it calls some other things, those are unspecified. No static checks, okay? But the runtime system is going to make sure that do compute only touches X, because that was the only thing that the caller had permission to, and the caller can only pass things it has permission to its callees. So you can make sure the whole call tree only accesses, you know, some piece of memory that you want to, which I think is kind of cool. Okay, so we're just, I think I'm at the end of my slot, so I'll just say we have an implementation of this. It's built on top of the Viper infrastructure. We extended it with some gradual verification techniques. So we extended their intermediate language with gradual specifications that have question marks. We extended the symbolic execution with an optimistic approach. And we had the optimistic checker generate dynamic checks for soundness at runtime. And then we connected that to a front end in a subset of C, which does the checking. So thanks to Jenna and my other awesome collaborators. And I'm happy to take any questions about the work.
Hi. Yeah, great talk. You mentioned all specifications need to be executable. I imagine there are some cases where you want a specification, it's not executable, but you'd be fine if it was only ever verified statically. Is that possible in the system?
Yeah, that's a great question. We have not thought about that. Yeah, I think, you know, if that specification only showed up in statically verified code and you know, it was never called from dynamically verified code, then and probably it never called out to dynamically verified code. Well, if it calls out to dynamically verified code, that's probably also fine, as long as like the interface to that dynamically verified code doesn't depend on that specification construct. So just thinking about it on the spot, I think you could do that, but we haven't worked it out. So yeah, it's a really interesting question.
Thanks.
Future work.
Hi. So I can imagine that I might write a specification for a function, and I don't know. I don't know something about. I might have a precondition that's not strong enough, and so I put a question mark in there, and I call it from some other function, and so I guess what you were saying was, in this case, this call kind of like eats all of the the dynamic version of the like accessibility predicates that I have around.
Yes.
But in this case, like, I mean, is there any way that I can distinguish, like, oh, I don't know about what ownership that I want versus there is some kind of bit of the functional part of the specification that's missing? Because I can imagine that,
yes.
I don't know, otherwise, you know, it eats all my tokens, and then I get an error, you know, because I lost all my accessibility predicates, and not maybe because I couldn't satisfy some precondition. I don't know if that makes sense.
Yeah, that's a good question. So one piece of that we've thought about, right? And actually one of the reasons we built on implicit dynamic frames rather than separation logic is that it separates the ownership from the assertions about the code. And so you can make assertions about the code and not say anything about ownership, leave a question mark for that. You can also talk about your ownership and leave a question mark for the assertions. So that part, it was an intentional design choice, and is you know, a very nice feature of the logic that we're building on, that we kind of, you know, inherit and built the system to work around. I hear another piece of your question, which is, what if I want to assert ownership of some heap but not make specifications, but I don't want to use a question mark for the specifications because that could include ownership. Yeah. We have not thought about that. Just spitballing it, I think it might be possible to do that with kind of a design pattern or a mode of use. of our system, but yeah, I'd have to check. I'd have to look at it in more depth.
Thank you.
Thanks.
Okay. So I was just going to ask, the difference between implicit dynamic frame and separation logic, which I think you already answered to some extent.
Yeah.
The other thing is you mentioned higher order function. I just like to point you to work that we did recently in FM24 on how to extend the logic to higher order functions. Yeah.
Excellent. Okay, yes, we would love to look at higher order functions. We have not done that yet. And building on an existing logic would be great. Maybe we can talk afterwards.
Okay, it's probably fine.
Okay. If you want, you can probably use Jonathan's laptop.
If I what?
If it's not going to last, you can probably use Jonathan's laptop.
No, I should be good.
Okay, our next talk is from Hazel, who's going to describe an extension to the work that Jonathan just presented with some really nice usability improvements that we've been waiting quite a while for. So.
Yeah, let me figure out what I'm doing real quick and I'll get back to you. Bruh. I promise I know how to use a computer, guys. Oh, I just started at the wrong side. That was a sneak peek. Okay, hi everyone. Thank you, Hemant, for the introduction. Like you said, my name's Hazel. I am presenting on formalizing a new syntax construct in gradual verification, and specifically how that kind of interplays with ownership and the challenges that poses in the face of ownership. And this is work I did with Long, one of Dr. Aldrich's PhD students, and Dr. Aldrich in my REU this summer at CMU. And so to get started, kind of for the motivation for this and the place it takes up in the existing literature, we're discussing unfolding expressions, which are, as you might be able to guess, a type of expression that you can use to more concisely and expressively communicate information about ownership when you're writing your specifications. And these are commonly used in real-world programs implemented in several verifiers. And we need to check that these are implemented in a way that's sound, because otherwise we don't know whether the verifier is actually checking the things we expect it to be checking. And so to address that, we are working on the formal semantics and a proof of soundness for how unfolding expressions are evaluated in gradual verification. And this is because gradual verification is a conservative extension of static verification, like Dr. Aldrich mentioned. This proof of soundness and the semantics will apply to both static verification and gradual verification. And so to get started with looking at precisely what an unfolding expression is and what it does and why we should care about them, we have some background we need to cover first. So to start, Viper, we're building on the Viper verification infrastructure, which is used for building static verifiers. It provides an intermediate representation, kind of like when you compile programs, except in this case, we use it for verifying programs rather than compiling. It also provides a symbolic execution backend you can use to statically verify programs in that intermediate representation language. And in Viper, we use recursive predicates to specify our data structures and encapsulate ownership over these data structures. So for example, these can just hold arbitrary facts. Like this is even predicate, we can just check whether an integer is even, and we'll get some more complicated examples that interact with ownership in the next couple slides. And one of the important things to note about these predicates and how we work with them is that they are interpreted using isorecursive semantics, which means that if we have a predicate, the instance of the predicate is different from the information that we have inside its body, which makes it difficult to reason about ownership when your accessibility predicates are contained inside other user-defined predicates. And we're building upon implicit dynamic frames, which is a variation of separation logic where you specify your heap ownership and content separately rather than together. And so to start discussing with the isorecursive semantics, like I just mentioned, we can have predicates like this that contain accessibility predicates to specify ownerships to data structures like this test struct. And we can see here, we have kind of distinct notions of what it means to have P of A and the accessibility predicate for the field F of A, even though we define these to be the same thing. And so to exchange between these separate notions, we use unfolds and folds, which will just take, unfold will take a predicate instance to the information in its body. And then if we want to get the predicate instance back from the information there, we can fold an instance of that predicate. And so this is relevant to ownership, specifically in this context, because like we said, these can contain accessibility predicates, which specify accessing heap locations. And then we can use these permissions inside the predicate once we've unfolded it, but not while the predicate is folded. And this is useful because when we write specifications, we need to make sure that they contain all the necessary permissions to be well defined so that we can execute them like Dr. Aldrich said. And so in this example, we have an accessibility predicate here. But to access it from outside of the predicate, we need to first unfold the predicate. And so to look at a little bit more complicated of an example for this, we're going to start with a linked list, just contains an integer and is a pointer to the next node in the list. And we are going to specify this with a recursive predicate. Like we said, this just checks whether the list is empty. And then if the list isn't empty, we make sure we have access to the two fields and that the rest of the nodes after this one also constitute a linked list using this predicate recursively. So this is really helpful for encapsulating ownership of our data structures, like linked lists. In this case, we can also do this with things like trees and other recursive data structures. This is using the notion of predicates that we talked about before, where these are self-framing assertions where we give all the accessibility predicates we need, and then we can specify some facts about our data structures. And so, this is just overview of what we said. And if we have an instance of this list n predicate specifying some list, we know that this predicate instance contains an accessibility predicate for n next. But if we're trying to use that accessibility predicate from outside of the instance of list n, we need to explicitly unfold that list predicate. So how do we do that from inside the same specifications? So I'll show you a little bit of what I mean. And assuming your list isn't empty, because that's not really a useful case to reason about here. So we have this accessibility predicate inside our list predicate, assuming it's non-null. And then here we are going to look at an example where this is a function that takes in a linked list and just truncates it by cutting off the rest of the nodes after the first one. And we have this in the post condition, the ensures clause there. We state that, if we take in a non-empty linked list, then the result will be a non-empty linked list, which only has one node. We specify that by saying the rest of the list after the first node is null. We also have the code for the function here, but we're mostly just going to be working with this specification and this post condition. And so, since the result is going to be non-empty, we need to specify that the rest of the nodes after the first one are going to be cut off of the list. And so to do that, we need to make sure we have access to the pointer to the next node after the first one. And currently, the accessibility predicate for nNext lives inside list n, like we said. So as we have it right now, this specification doesn't verify. Although it makes sense in terms of defining the actual functional behavior of the program, we don't have ownership of the nNext field. because that accessibility predicate lives inside the list n predicate instance. So to address that, we can use unfolding expressions, which allow us to temporarily open this list n predicate, look inside, and take out the permissions we need to frame the evaluation of the expression, and then refold the predicate nicely when it's done. And I'd also like to note that these are a thing that are used in real programs, like real-world verified programs. So for example, if we're using the Gobra verifier, Go has a verified standard library, and it also has verified Scion, which is a project to verify the Scion routing protocol. The syntax here looks different from what we're looking at, just because this is Go and the Gobra verifier. So like, don't worry if it looks weird, that's normal. I don't know Go, so I'm not really looking into it that hard. But in this example, we have an unfolding expression here like we've been looking at. This comes from the implementation of multi-precision signed integers in verified Scion. And the predicate we're unfolding here is this x.mem predicate, which just specifies access to all the underlying memory locations in the representation of the multi-precision signed integer. And so to kind of address why we need to formalize this in order to, build upon, to show the soundness of the verifier and how we evaluate unfolding expressions, these haven't been included in a proof of soundness or a formalization of the semantics in any static verifier yet. We do have a formalization for certain parts of the Viper verification infrastructure via a formalization of gradual verification previously, but having a formalization that includes this will help us ensure that any implementation is done correctly, because we need to make sure that the implementations of the verifiers we're working with are sound, so that we're sure when a verifier passes a program that the program meets its specifications. And so we're going to look at this in more broadly than static verification, the context of gradual verification. Dr. Aldrich already talked about this. This will mostly be a recap, which means I'm going to hand wave some things he talked about a little bit. We're going to discuss the formalization and the theoretical aspects more than the implementation of it as well. So we're going to look at the same example with truncating a linked list, and we're thinking about fully specifying this program and writing this full specification up front. If we do this, we've got a high upfront cost for developers. Like he said, it's not super incremental because you have to have this full specification before you can debug. So to address that, gradual verification is introduced to allow you to write explicitly partial specifications that are backed by adding runtime checks wherever necessary, and we can just leave these blank. We can also add static information as we go on to decrease the performance impacts of runtime checking and to continually work towards a full specification. And so we've chosen gradual verification as the context for doing this work because ownership is kind of more interesting to reason about in this setting. Since we have to think about both static and dynamic checking, you have to keep track of the owned heap locations at runtime and while statically verifying, which is actually different in those both cases. And we also have to think about the fact that predicates are interpreted differently at runtime than they are during static verification, which we'll also discuss more in a minute. And since gradual verification is a conservative extension of static verification, if we formalize and do a proof of soundness for gradual verification, it'll also apply to static verification, which is super helpful. And like I said, this makes ownership a little more interesting to think about. And so specifically on that, we can have the partial specifications backed by runtime checks that can include accessibility predicates. And we also need to keep in mind framing. Framing is kind of our why we need to worry about ownership when we're thinking about gradual verification. Before we check any of our specifications, we need to make sure that they have ownership of all the fields they need to properly be checked. Like Dr. Elder said, we need to ensure all our specifications are executable before we go and check them. So framing is how we do that. So some examples of predicates that aren't properly framed, or specifications, sorry, that aren't properly framed. If we just have, access to the field F of the object X or the field G here, neither of these are self-framed because we need to make sure we have access to the field F of the object X ahead of time. So to do that, there are several ways we can make this self-framing. We can either add an accessibility predicate specifying access to F, or we can use the imprecision, the question mark, and this can be strengthened into the accessibility predicate. And so to look at an example that kind of motivates how we develop the evaluation semantics for unfolding expressions, we're gonna kind of go over the formal semantics, or well, an example that demonstrates the formal semantics for how we've defined these. This was already implemented in a past extension to gradual verification, but having the formal semantics, like we said, helps us check the implementation. And it actually did do that because we found a soundness bug in the verifier having these formal semantics. Yeah, and so we're building on a past formal system for gradual verification because there's a past formalization using symbolic execution. And with this symbolic execution system, there are 4 kind of fundamental operations we can do with our expression statements and specifications. So the first and last one, evaluation and execution, kind of relate to symbolically running our code, where we are executing our programs with symbolic values rather than concrete ones. And the middle 2, produce and consume, relate to what we know and how we interact with the specifications we have. And we're specifically going to be extending this symbolic evaluation one, since unfolding expressions are a kind of expression. So we're going to look at how we evaluate this unfolding expression in the context of the truncate example we've already been looking at. So we know before we even start evaluating this, we know that list n holds because we've added it before the rest of this post condition. So we have an instance of list n ahead of this, and now we can start evaluating. So first thing, we're going to open up our predicate to use the facts inside when we evaluate this expression. So when we unfold this list n predicate, we lose access to our instance of that, but we gain access to n next and the other facts that are specified inside the predicate, like the integer value of that node and the rest of the linked list. And then now that we have these permissions, we can evaluate this expression without an error this time. So we can check whether the next node is null as specified. And then going from there, after we've evaluated the expression, we can refold it, and this loses the information about ownership we had with the accessibility predicates, but we get our instance of list n folded back, so we're still satisfying our post condition. And so that's kind of how we go about evaluating these broadly, but there are some specific challenges we've encountered in building this formalization up to fit that intuition. And so the first one we can run into is we can have issues with unbounded recursion when we are evaluating unfolding expressions in this way. So in this example, we can see we have a predicate on a list, and we're not going to focus that much on what this does specifically, but the one thing to note is that we have another unfolding expression in here. And so when we try to use an unfolding expression with an instance of this predicate, what will happen is we'll unfold an instance, which will want to unfold another instance applying to the next node, and so forth and so on. And this won't terminate in static verification because we have symbolic values rather than concrete values. So at each step, it'll branch depending on whether the predicate could have terminated or not. So at a certain point to address this, we just cut off the recursion. I like to think of this as we just kind of block it off and you can't go any further. So we keep track of the predicates you've already seen when you're evaluating one. And after a certain depth of mutual or simple recursion, it just gets replaced with a symbolic value that doesn't carry the same information. This approach is theoretically incomplete, but this isn't really something you observe in practice because you would need to manually unfold to the same depth that the recursion gets cut off at, which isn't a super common use case you're working with. Another one of the challenges is with isorecursive and equirecursive framing. So like we mentioned, isorecursive framing is used with the static semantics for unfolding expressions, but we need to think about predicates differently at runtime. So we use equirecursive semantics where predicates are equal to their full unrolling at runtime rather than having them be distinct from the information in their bodies. And this means we don't really need to worry about things like folding or unfolding predicates at runtime. So checking whether our expressions are properly framed with ownership of the appropriate fields can be more difficult, especially when working with unfolding expressions in this case, because we need to reason about it super differently statically in the isorecursive case than we do at runtime in the dynamic case. And then one more of the challenges we've encountered along the way is that unfolding expressions kind of combine predicates and expressions in a way that we haven't seen in the rest of the formal system for gradual verification yet. And this can make it more difficult to work on our proof of soundness because we need to avoid circular reasoning with our proofs. And since predicates already rely on expressions, since our predicates can contain heap-dependent expressions to specify, we need to make sure we aren't circularly reasoning between our lemmas about predicates and our lemmas about expressions. And so for future work, continuing to expand upon this, like Dr. Aldrich showed, gradual verification has been kind of actively developed for a long time. And so there's always more to build on with interesting implications and repercussions we can discuss. So the first thing we're continuing to work on is our proof of soundness. We're using a progress preservation formulation for soundness, similar to the one we see with type systems commonly. We change the definitions of progress and preservations so that it applies to the verifier, but we still have similar principles here. And we also have to update the rest of this proof of soundness since there is one, but it hasn't included unfolding expressions yet. And we've done a lot of the lemmas for expression evaluation, but there are also some ways adding unfolding expression has changed the rest of the formal system that we have to account for. And so for the broader impact of this work, unfolding expressions are super useful for increasing the expressiveness of verifier, and we see them in real world programs with verifiers like Gobra based on Viper as well. So having this formalization can help us check implementations to make sure everything is sound. In terms of our long-term vision and our higher level vision for working on formal verification, this isn't something we see super likely to be used manually in the future, since we're working towards providing more intuitive abstractions for verification so that developers don't have to manually work with things like this. And one of the things we are considering working towards to uphold this is bringing gradual verification into a language with a type system that contains ownership info. So like, for example, Rust, I couldn't get away with not mentioning Rust in this workshop, I fear, but the type system info from Rust with the borrow checker can automate a lot of the specifications that developers have to manually write, like folding and unfolding predicates, and it already has a strong formal verification community. So bringing gradual verification into Rust could help build a new level of abstraction to make verification simpler and more intuitive for developers. And that's all. Do you have any questions?
I guess I can start. One thing that this sort of made me think of, and this might be like totally off base, is like what happens with unfolding expressions and ownership is you like take temporary ownership of like the thing inside a predicate and then give it back. And that has like this kind of borrowing flavor almost. I was wondering if you'd given any thought to the relationship between those things.
Yeah, that's something we've talked about at like a high level. but not like super in the weeds with that yet. It's something we've like pondered a little bit, but not in depth yet. But yeah, there is like an interesting connection there. I'm thinking of a paper, but I can't remember what it is. But yeah, like with ownership type systems, the notion of like unfolding and folding predicates is similar to like how you how you would when verifying like pack and unpacked data structures, something to that effect. But yeah.
Sure. Yeah.
Great talk.
Thank you.
One sort of technical question I was curious about is that we've just seen over the last two presentations a equirecursive and an isorecursive take in the same system. How does that interact?
So that's a really good question. Thank you. So with the equirecursive and isorecursive semantics, so you have to make sure that there's that these kind of move together in step between the static and dynamic semantics when you're proving soundness. So what we do to make sure those interact correctly is we have to define a notion of correspondence between the dynamic semantics and the static semantics, so that we can check whether, like, if we have a valid state in static verification, it corresponds to one in dynamic verification, which is where we handle most of the interplay between like connecting the isorecursive and equirecursive interpretations. Does that answer your question? Yeah. Okay. Awesome.
Hey, thanks for the great talk. At the end there, you were talking a bit about how it's like inconvenient to actually write all of this stuff manually, right? And I was thinking, rather than working at an entirely different level of abstraction or something, is it possible to just do some sort of like, I guess, inference or like automation there? Because at least in the examples that you showed, it seems like since like the reason you need the unfolding is just to get the access predicate you need to satisfy like another thing that you want to mention, and is that straightforward enough that you could just like have the system automatically like figure out what it needs to unfold to get that, or is it just like way more complicated in practice?
There is some like more broadly like in the space of formal verification. I know there's work on like specification repair and like specification synthesis. I know like specifically in the context of gradual verification, I think Jenna DiVincenzo, who Dr. Aldrich mentioned in his talk, has also been working on some things to that effect recently, but I'm not super sure about that. I'm certain there's like things you could do in that space. I'm just not super sure how it would look different for gradual verification yet, if that makes sense.
Okay, thanks.
Yeah.
All right, let's give the speaker another hand. And